So, again, I'm around tomorrow after school if you have questions, last minute ones. Let me talk a little bit about the written section. And same deal, you can write this down if you want, or I can print this up for you at the end. I'm good either way. Okay? Some key ideas. So what are you going to see in the written section? You're definitely going to see some stuff where we are in orbits. And if they mention orbital path or in a stable orbit or in orbit, what's the first thing? Well, to find V or T or anything else like M or R, whatever, we start out by going gravity equals centripetal. Okay? From there, there's 1,000,001 permutations. Hey, if they want me to find velocity, okay, well, the left side never changes. So to find V, it would be big G, big M, little m over r squared equals mv squared over r. And yay, a mass cancels, 1r cancels, I can find V. If they want me to find the period, well, I would go big G, big M, little m over r squared equals m for pi squared r over t squared. Hey, once again, m cancels. Unfortunately, the r's don't. You have an r cubed. And I can find the period. Or I can find the radius. Or, heck, I could even find the mass of the planet. If you tell me how high and how fast we're orbiting in, I can tell you how big the planet we're orbiting it around is. Solve for big M, because that doesn't cancel. I'm not going to ask you to solve for big G, because that's 6.67 times 10 to the negative 11, which is kind of pointless. But I could also ask you to solve for R. Hey, how high do we have to be? What's our orbital radius to stay in stable orbit? So that's when we're in stable orbit. As an example. Find the orbital period of a satellite with an orbital radius of 3, 4, 5, 1, 2, 3, 4, 5, 6 meters if they're rotating around the Earth. That's way too many zeros. Let's do, I want to be, let's go 5 zeros. Okay? A lot of this is calculator work, so make sure you're familiar with your calculator. Be careful. And, hey, we're in orbit, so Itzel, I would start out by going that. And believe it or not, that'll get you 1 mark, because you've recognized the correct approach. Gravity is always the same. Big G, big M, little m over r squared equals, and they said period, so I would use this one. Not r squared, Mr. Duke. 4 pi squared r over t squared. Yay, Jessica, mass cancels. I get the t by itself. I think the t squared moves up to there. Now it's on the top. The gm moves down to the bottom. The r squared moves on top of this r. Now it's going to become an r cubed. Yes, Shannon? Is that okay? In fact, you end up with this. T squared equals 4 pi squared r cubed all over big G, big M. Hey, how'd I get rid of a squared? And take it from there. Are you guys okay with your calculators going from this point on? Or do I need to actually solve it? You're okay? Itzel, you're good? Okay. Oh, or I could have given you the same, but instead of find the orbital period, here's the radius, I could have given you the orbital period. What's the radius? You'd still start out the same way, but you get the r by itself. You get an r cubed by itself. This is the one where you ended up cube rooting when all was said and done. Okay. The second type of cosmic question is the work question. Not in stable orbit. Keyword, lifted. Or type this, how much work, or those are some of your triggers. Okay, doesn't mention orbit. So if we're doing a work question and we're not in stable orbit, work equals the change in potential. Work is always the change in potential plus the change in kinetic, but usually if we're lifting you into orbit, what we're implying is you started and ended at rest. Can I use MGH here? No, got to use the cosmic one, right? Use potential energy equals negative big G, big M, little m over R. Example 2. How much work to raise a 2,500 kilogram satellite to an, can I do underline here? I can. Altitude of 4 times the Earth's radius. Once again, I'll get us started, but we won't finish, because I'll assume you're okay on the calculator stuff. Work is force times distance. Can I use force times distance here, Kara? No, because the force is changing. The further you go from the Earth, the weaker gravity gets. And force times distance only works when the force is not changing. Work is also the area under a force versus distance graph. Kara, do you see a graph here anywhere? Nope. Our third definition was work is change in potential plus change in kinetic. We called that the work energy theorem. The word raise, is that a synonym for lifted? So I don't think we're in a stable orbit. In fact, let's assume starting at rest, ending at rest. Oh, and by the way, so here's the Earth. Our altitude is 4 times the Earth's radius. What is our final radius? Yeah? Altitude is from the ground surface. Yeah. So you know what? We're going to have to include one more radius. The actual radius is 5 times the radius of the Earth, because the altitude is 4 times plus one more. There is at least one question where I give you an altitude. Usually I give you the orbital radius, or I just say the radius. I can't say orbital radius because we're not in orbit, but I could say lifted to a distance of whatever from the center of the Earth. That's a radius. But there is one question on your test where I do something like to an altitude of, oh, and I'll even be more specific. It's not 4 times the Earth's radius. It's either 3 times the Earth's radius or 2 times the Earth's radius, which is why I had to make up, in my example here, 4 times the Earth's radius so that you would see a question that wasn't on the test. It's overkill. Could you take it from here, Emily? Oh, it would be... negative big G, big M, little m, all over R final, minus negative big G, big M, little m, all over R initial, where R initial is the radius of the Earth, 6.38 times 10 to the 6th. R final would be 5 times radius of the Earth, because it's 4 altitudes plus one more. Is that all right? It's going to be one like, how far from here to here? 1, 2, 3, 4, 5 radii. Right? That's your final radius from the center of the final distance from the center of the Earth. Because it's an altitude. Right, Brett? This is what you asked. This is because it's an altitude. If I didn't say the word altitude, and I'll show you an example of the wording of one in a second. Did I use the same numbers as last time? 2,550? I did. 4 times the Earth radius? I did. If you want to try this at home for study, I think the work, because I did this last year, ended up being 1.28 times 10 to the 11 joules. That's lifting something. Here's what I'm also going to ask. How much work to put the 2,550 kilogram satellite into a stable orbit at an altitude of 4 times the Earth's radius. The reason I like this question is just not because it's nerdily interesting, although it is not just because it's nerdily interesting, although it is to me. This really covers almost the whole unit in one question. What are they asking me to find, Shannon?
Holly Burrows, please come to the office. Holly, come to the office, please.
What do you want to find first? I can't hear you, sorry? Well, I don't have a potential. I have something in front of it. Gotta be fussy yet. Okay, change in potential? What's change in anything? Okay, so we're going to find change in potential first. Which is going to be negative big G, big M, little m all over R final minus negative big G, big M, little m all over R initial. Yeah? Which is going to be negative 6.67 times 10 to the negative 11. Sheesh. Mass of the Earth, 5.98 times 10 to the 24th. Sheesh. Mass of the object, 2550. Sheesh. Divided by... Now, if we're at a stable altitude 4 times the Earth's radius, how far are we from the center of the Earth? 5, right? 4 altitudes and 1 more to the center. 6.38 times 10 to the 6th. Squared? No, not in the energy equation. Plus, because it's minus, minus is a plus. Same thing, same thing, same thing, all over. Don't do that on the test, but in the interest of time here, we'll use ditto marks. Initial radius. Hey, where are we starting off? What's reasonable to assume? They didn't specifically say it, but I think we can clue in. Where are we starting off? On the surface of the Earth. So initial radius is just 6.38 times 10 to the 6th. Would I type all this in at once? It's no. In fact, I would do the whole first term, which I will right now. Negative 6.67, scientific notation button, negative 11 times 5.98, scientific notation button 24 times 2550 divided by bracket 5 radiuses. That's how much energy we have final. Negative 3.1884 times 10, negative 3.1884 times 10 to the 10th plus, and this is why I would type these separately. If you have a half-decent calculator, you can bring up your previous lines somehow. Change the negative to a positive. That's the same. That's the same. That's the same. Oh, and I just want 1 radius down there. It's about as lazy as you can do this, but also I've minimized the chance of me doing dumb calc mistakes. I go uber careful on the first one, and I can really relax on the second one. How much energy do we have on the ground? 1.5942 times 10 to the 11th. What's my change in? This take away that, or this plus negative that. Plus negative 3.1884 4, scientific notation button, 10. That's the amount of work to lift it up there. 1.2754. 1.2754 times 10 to the 11 joules. Hopefully that's what I told you the answer was earlier. Yeah, 1.28 times 10 to the 11th joules. It's also the answer to this question right here, because here we just asked how much lifted up here. We just recalculated it. That's that, Shannon. Now what do we got to find? Yeah, changing kinetic. Okay. What's changing anything? Let's assume we start out at rest. So this is just going to be a half little m, because it's the mass that's moving, the satellite that's moving, v final squared. Of course, the problem is, how fast am I going? Don't know. Oh. What word is that right there? Fg equals Fc, right? G hasn't changed. Big G, big M, little m over r squared equals m. Oh, I want orbital speed, so I'll use the mv squared over r. We've seen this a few times. Hey, an r cancels, woohoo! An m cancels, woohoo! One r is still left behind. We end up with v squared equals big G, big M over r. How do you get rid of a squared? Oh, but you know what? I don't think I want to get rid of a squared, do I? Do I have a v squared in my original equation? Oh, heck, let's just replace all, let's save ourselves some square rooting and then re-squaring. Put it right there. We get this. The change in kinetic is equal to a half little m, big G, big M over r. This is also where we noticed, Emily, turns out the kinetic energy final just happens to be my final potential, but positive in half of it. Because wasn't your final potential big G, big M, little m over r final, but negative? Not. Yeah. But, okay. The reason that's also kind of nice is, look, I got most of these numbers. If I go second function, enter, second function, enter, I got most of these numbers right there. Big G, do I have big G? M, do I have M? Little m, do I have little m? R, do I have R? A half, do I have a half? Ah! That's convenient. Yoink. 7.971 times 10 to the 10th. Kara, do you have a question? Ask. What letter's right there? What letter is going to be right there then? Ah, so you're saying, hey, Mr. Dueck, dumb cup, this is wrong. Which radius do I want to use? The final radius. Are you saying that should be that? If you were, I'm impressed, because I missed that. Yoink. How about 1.594 times 10 to the 10th? 1.594 times 10 to the 10th. Let me check, does that match my number? Yes, it does! Total work, change in potential, change in kinetic, which ended up being 1.28 times 10 to the 11th joules. This number plus that number. Yo. Yeah, see, if you wanted to plug it in as a number, you could go G times M divided by final velocity. Get a number and put it right in there. I just noticed since the V squared is in both, why don't I just plug in the algebraic expression? Because that's what I type on my calculator. Why not do it all in one fell swoop once? Nope, because it's V squared matches V squared. Is that okay? Oh, sorry folks, I read the wrong page. I'm apparently more tired than I thought. The actual answer you're going to get is not 1.28, it's going to be 1.44 times 10 to the 11th. Read my own notes. Okay? So that gives you an example of, hey, for an orbit, Fg equals Fc. Have I preached that enough? We're clued in? Yes? If they say how much work, change in potential, change in kinetic, maybe change in kinetic 0, stable orbit not, I don't know. Then there were questions where there was a change in height conservation of energy, change in height or change in speed, but work isn't mentioned, and we aren't in orbit. C. Suppose a satellite has a launch velocity of 8450 meters per second. How high from the center of the Earth can it reach? Ignore air resistance. So now I'm giving you its launch speed. Boom. How high can it get? Does this question imply that we're in a stable orbit? Far from it. I think it implies it's going to fall back down. Okay, so am I going to go Fg equals Fc? No. Does this question ask how much work? What is this question asking? How far? This is a job for conservation of energy, because is there a change in height, Itzel? Yeah. Is there a change in speed? Kinetic initial plus potential initial equals kinetic final plus potential final. Are any of these 0? Yeah. Which one, Jess? Yep. Definitely not initial this time, because they're telling us our launch velocity. Oh, my initial potential, because I'm not using MGH, is not 0. If I was using MGH, I can't use MGH because G is changing. So this is going to be a half mv initial squared plus negative big G, big M, little m, all over R Earth, because that's my initial, equals negative big G, big M, little m, all over R final. You put it in block B? Are you block B? No, you're block A. Put it in block A. Thank you. Thumbs up. Hey, what are they asking me to find here? There is no height in this equation. What are they asking me to find in this here equation? Our final, right? Isn't that my actual? Now, what if I had said, I said distance from the center of the Earth. What if instead I had said find the altitude? Once you found this, what would you do with this answer at the very, very end to find the altitude? Subtract the Earth's radius. I don't remember if I do one of those or not, but I don't think that's a big stretch to ask. In fact, that's really what we'd be more interested in. We'd like to know, how high did it get? We measure our heights from the Earth's surface, not from the middle of the Earth. But the math works from the middle of the Earth. How would I solve this? I don't think I would try and get the R by itself. I think I would crunch this whole left side first. Same satellite. So I would go 0.5. Oh, no, wait a minute. Is there a little m right there? Is there a little m right there? Is there a little m right there? Are you telling me there's a small mass in everything, Itzel? Are you telling me that your head's sideways because you're that tired, Itzel? What can you tell me about the little mass, Itzel? They what? Well, that's good. I was about to do extra work. 0.5, 8450 squared plus negative 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, all divided by 6.38 times 10 to the 6th. That equals negative big G, big M over our final. By the way, Emily, do I want the final radius to be a positive or negative answer when all said and done? Positive. What's right there? I'm hoping this whole left side also works out to a negative so that my negatives do what? Cancel. In other words, I got a bit of a built-in error check. If I add these two together, I get a positive answer. I've made a mistake. I'd have to have, right? Are you okay typing that into your calculator? Are you okay typing that into your calculator? Would you be okay then adding those answers together? Then I'm going to skip that step and simply jump straight to it. I got negative 2.68 times 10 to the 7th. Negative big G, big M. I think, Kara, now I would try and get the R by itself. In fact, because now I have one thing equals one fraction. This is straight cross multiply. The R moves up there, that moves down there. The final distance from the center of the Earth is going to be negative big G, big M all over negative 2.68 times 10 to the 7th. So there's kind of an example of where I'm going to use conservation of energy. The other place you would use it is if I drop an object from a high altitude and have it come either crashing back down to Earth or falling through, several 100,000 meters. So you have an R final and an R initial. And how fast is it going when it gets to the bottom? In that case, your KE final would not cancel and you'd be solving for V final. Is that okay? Yeah, no? I was surprised. I thought there'd be way more people here. That's okay. You guys are worth it. Mr. Dueck, where'd you... Oh, there it is. I like this next question. I like this next question. I like this next question. This next question is a nice question. Because it's an amusement park ride, and it's circular, and it's cool! Can you get any better than this? On one of my tests, I'm going to ask you a question about the Gravitron. It's a popular amusement park ride. Okay. Cody. Sure thing, sir. So I love this. If you haven't clued in by now, Shannon, I'm nuts about amusement park rides. And I hope they're great examples of good physics for you guys because it's one of the things most of you have been on. Haven't been on this one ever. They used to. I think they only have it now at the P&E, but it's not at Playland. I'm going to have to go to the P&E and pay the money just for that. Okay. It says, draw a force diagram and write force equations. Okay. What are the forces acting on this? Get the obvious ones. Which way? So, you know what? I'll draw the diagram right here. Are they standing in place? Yeah. So can that be the only force? No. There has to be something here. What? Let's hold off until let's go process of elimination. What else? There is one more force. You know how I know? What path is this person tracing out? A circle. Where must my net force always be pointing if I'm moving in a circle then? There has to be a force there. Which force is that? Give you a hint. Huh? It's the ground. It's the wall. It's like the ground has been tilted. In fact, this is also how we faked gravity. We said it was the normal force on a spaceship. If you had a space station that was slowly spinning, the normal force would become Fg in that case. What's this one? By the way, don't you dare put Fc on here. It never shows up. And I will ask you to draw a free body diagram, some kind of circular motion free body diagram on the test, right? Itzel. What? Is it friction? It is. Now here's how you can reason your way there as well. What's the angle between these two here? Weren't normal and friction, when we were horizontal, almost always 90 degrees? Yes? And in fact, it was normal pointing up, friction pointing backwards, normal pointing right, friction pointing upward. Yeah, it's friction. Okay? So what kind of questions could I ask? Well, if I gave you the radius, let's say, I'm just making this up, 2 meters, is that way too small? Anybody been on this ride? What's the radius, rough guess? So distance from you to the center of the ride when you're sitting on it. Can you remember? Is it from here to you or further? From me to you or further? About like this? One meter stick, 2 meter stick, 3. Yeah. Probably between 4 and 6. I'll go football. Okay. Hey, let's write force equations. Who's winning? Right? Now, this also means that either of those are now fair game. It would depend on whether I said, hey, how fast is the ride spinning at? Or if I said, hey, what's the period of the ride? Or if I gave you the speed that the ride was spinning at? Or if I gave you the period of the ride? Problem. What's the normal force? Don't know. Look at my free body diagram. What other force equation comes out of this free body diagram? What two forces are equal? Okay, we also have this, right? Friction equals what times what? I don't know the normal force, but wait a minute. That's not the circular motion equation. This is the circular motion equation. I don't know the normal force. Oh, but look. I know another equation that will let me figure out another expression that's the same size as the normal force. Get the normal force by itself. What is it? Yeah. Okay, this is also cool because in this case, we're actually using the friction to figure out the normal force instead of the normal force to figure out friction. And now I can plug that there, and whatever information I give you or ask for, you're good to go. Most kids, when they see this, they'll say, oh, normal force is mg, because that's what it was for most of the year. Did you, in fact, I yelled at you guys, I think, this year when we did the forces unit. I said, you have never, ever heard me say normal force is mg. You've always heard me say friction is mu times the normal force, but I don't know the normal force. Look. I know another force the same size as the normal force, and I do. And I need mg. Turns out it's mg divided by the coefficient of friction. Okay? Kind of a nerdly cool question, I think. And it all depends now. Not enough friction there in that case. needed more friction, otherwise, and it wouldn't have spilled. But anyways, thankfully it's still all dry, yes. So from either this or this, I could either give you the velocity and say find the radius, give you the radius and say find the speed, give you the radius and say find the time, give you the time of rotation and say what's the radius, or heck, once I tell you all that, actually, you know what? I think you get this. Brett, you said you went on this ride? Did you have to step on a scale before you went on the ride? How come? Oh, love that. There you go. So anything there is fair game, except I guess not the masses, because the masses cancel. Oh, and G is 9.8, so I probably wouldn't ask you that. I guess I could move it to Mars or the moon or another planet and tell you the values and say, hey, what's G on this planet? That would be nerdly cool. I don't think I did, but oh, that would be great, because then once you know G, I could talk about gravitational field strength, and you could find the radius and the mass of the planet later. But no, I didn't do something like that. Last thing I want to talk about a little bit here is lowercase g, which is what we called gravitational field strength. That's not the last thing. Can you also make sure I talk about vertical circle Ferris wheel questions? What's G on the Earth? 9.8 units. There's two ways to measure the units. What are the two ways to measure the units? Meters per second squared, or now here's how you can figure it out. Right? Get the G by itself. Jessica, what do I measure force in? What do I measure mass in? Oh, it's also newtons per kilogram. It's got to be. Right? That's actually, I rethink that every time quickly in my head, right? Because 1 second of thinking, I'm not going to memorize that then if I can figure it out in 1 second. What's the equation for calculating G, though? Yes, it's that. This is sort of on your formula sheet, but not blatant. What's the equation for calculating G? Yeah. No second M, right? Now, here's how that works. Is that gravity on the Earth? Is that also gravity on the Earth? Yeah. What do you notice about the little m's? Oh, and now you have an expression for G. Okay, so is that on your formula sheet? Not blatantly. And little g is the gravitational field strength. It's how strong gravity is tugging every Newton per kilogram, how strong gravity is tugging at that particular point or on that particular planet. So either I can tell you, hey, you're at an altitude or a radius of blah, 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 blah. What's the gravitational field strength here from the Earth? It's going to be less than 9.8, but it won't be 0. Or I could tell you what the gravitational field strength is and say find the mass of the planet, or find the radius, our distance from the planet, how far are we from the planet. Okay, so there's definitely going to be a couple of questions that use that, gravitational field strength. Last thing I wanted to talk about, and then I'll do specific questions from the review, was Ferris wheel type questions. And I think I had one of those here too. Did I do it? Yeah, I did. Great. Click. Yoink. Okay. Student is on a 15-meter diameter Ferris wheel, rotating at a constant rate with a period of 13 seconds. A. Find the normal force at the top. And B. Find the normal force at the bottom. Okay. Question, Chad? No? Sure. Okay. Caitlin, let's do the top first. Okay. And I'll see if I can fit this all on here. I'll do A here, and I'll do B over here, and that way I can fit it all on one screen. At the top, what are the forces acting? Get the obvious ones. Which way? What else? Well, now you have to imagine which way is your chair facing. In a Ferris wheel, your chair is still facing up. So which way is the normal force pointing? No. Up, right? Chair's pushing you up still. Why did I draw the normal force smaller? What path am I tracing out? So where must my winner be? Towards center. What if you're in a roller coaster? In a roller coaster, when you're in a loop, is the chair facing up? Facing down. Which way is the normal force if I give you a roller coaster question? Down. And it would be winner plus winner. Here it's going to be winner minus loser. And that's your free body because FC doesn't appear on your diagram. It's going to appear in your equation. I think the normal force would be equal to mg minus FC. Right? The normal force is going to be equal to mg minus... Am I going to use the one with... Oh, they gave me the period. So I'll use the m for pi squared r over t squared. I know the radius. I know the period is 13. I could calculate the normal force. By the way, normally, no pun intended, normally what's your normal force? What are you all feeling right now as your normal force? What are you all feeling right now? That, right? mg. Okay, so here's my question. At the top of a roller coaster, at the top of a Ferris wheel, you would feel lighter or heavier? Heavier? Really? Jessica, why lighter? Why obviously lighter? This is what you normally weigh. This is what you normally feel. And we're taking something away from it. Right? You're going to feel lighter at the top. In fact, the faster you're going, the smaller your period, the lighter you'll feel. Is there a ride at Playland where you do a loop where you do stay on the outside? I don't think, aside from the Ferris wheel, a quick loop. Because the Enterprise, you're on the inside too. And on the Revelation, or Revolution, whatever it's called, you're also on the inside. You flip. I don't think there is. Because that would be cool. The Enterprise? Well, I'm not sure if they got rid of this or not, but I really have no idea what that was at all.
Michelle Bouchard, please call the office. Michelle Bouchard, call the office, please.
It's a new dance, Mr. Dueck. It's called the Nerd. Does that make sense? You would feel lighter, right? Hey, what about at the bottom? Well, okay. What are the forces? Get the obvious ones. Which way? Thank you. What else? Normal force. Which way is the chair pointing? Up. Normal force is also still up here. Why did I draw the normal force bigger than gravity? What path is this person tracing out? So where must the net force be pointing? Toward the... This is going to end up being winner minus loser equals FC. In fact, you get the normal force equals your normal gravity that you're used to feeling right now plus FC. Oh, you feel heavier at the bottom. Because remember, we've said to you guys, what you think of as your weight is really how hard the chair is pushing against you. Our bodies are bad accelerometers. What you think of as weight is really the normal force, not gravity. How do I know? Because when I jumped out of an airplane, I mentioned I jumped out of an airplane. When I jumped out of an airplane, was I still feeling gravity? Absolutely. Was I feeling a normal force? That's why I felt weightless. That's what I felt. Right? Same with the astronauts in orbit. Are they not still feeling gravity? We said they are. They're in free fall. So why do they feel weightless? What don't they feel? Normal force. Okay? So, and I'm assuming you can crunch the numbers. It would be mg plus m4 pi squared r over t squared. They gave me the mass. That's good too. Also, again, then remember, I can't remember if I do a roller coaster loop on the test where you're on the inside. If you were on the inside, it would be gravity plus normal force at the top. And it would be gravity plus normal force at the top. It would be centripetal minus gravity at the bottom. By the way, who's in calculus here? Who's in calc? Just you? Okay. What if you stopped? What would your period be if you stopped completely? The period would approach infinity, would it not? Because you're not moving at all. And if you put infinity on the bottom of a fraction, what does this work out to? The limit for you, 0. Oh, if you're stopped, you just feel mg. That actually is a kind of a little proof of why the limit as x approaches infinity when x is on the bottom of a fraction has to approach 0. You're the only one in calc here? Wow. Shame. Questions from the review. Individual questions you would like me to go over. Hints and things like that. Yeah. Number 12, from which review? From this one? Because I gave out 2, right? Here? How much work? Yeah? Okay, we did one just like this, but I don't mind doing it again. Are we in orbit? You know how I know? First of all, there's kind of a lift implies no. And in fact, I think this one is going to be and no change in kinetic, because this doesn't suggest that we're then moving after. I think we're, invisible angels are holding us there. What's changed? Anything? This is going to be negative big G, big M, little m all over our final minus negative big G, big M, little m all over our initial. Negative 6.67 times 10 to the negative 11. Yes? We're on the Earth. 5.98 times 10 to the 24th. 40,000 kilogram satellite. That's a big satellite. Also, I can tell I'm going to run out of room. So let's do this, Mr. Dueck. What's a minus minus the same as? It's okay. Oh, got to divide by r final. Now it does say to a height, so the radius is going to be the radius of the Earth plus the height, right? Same thing, all over radius of the Earth, because that's what we're starting out at. You did that? You think I made a mistake? Did I? Let me try this whole thing again then. You might have earned yourself $1. Money, 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 money. Degrees shouldn't matter at all. We're not doing any trig. Right, Brett? Okay, that's the first number. I get negative, final is negative 2.388 times 10 to the 12th. Double check. That's correct, that's correct, that's correct, that's correct. That's negative 2.388. Negative 2.388 times 10 to the 12th plus nuke the negative, nuke the altitude, 2.501 times 10, 2.501 times 10 to the 12th. So it's that number, take away this number. I hit the right button. Did I pick A? Is that what I did? Look at my answer key. Yeah. Now, I don't quite like this because when I carry a few extra sig figs, it's actually 1.13 times 10 to the 11th, but clearly that's the answer they want me to pick. I'm guessing they rounded off a bit more than I did. You know what? I didn't add the radius. I didn't put the... So there's a typo there. Is that what you're saying? That I agree with. So I'm going to go like this. Right click. Oh, reference letter for Caitlin. I already did that. Woohoo. Fix number 12 on circ motion review. R is wrong. Sleep. Today is Wednesday, right? Oh, heck. Let's see if I can get to it in 5 hours, or else I'll get to it tomorrow. That was it? You know what? If I got $1 on me, I'm giving you $1 for that. Here you go. You earned a loonie. It's right there for you to take. It's yours. Let me go check my original. Unless I fixed it already in my original and forgot to fix it on the PDF when I forgot to go reprint as a PDF. Let's see. Because here's my actual, the ones that I did in Microsoft Word. Load. No. Oh, no, you know what? 6 point, it is right. 6.68. There is a 6 there. 6.38. There's the first, there's the R initial. But when you go 6.38 times 10 to the 6th plus 3 times 10 to the 5th, all that happens is that 3 gets added to that 3 and it becomes a 6. I did do it right. I'm taking that money back. Let's double check. Oh, I closed it. Yeah, I did do it right. Nice try, little... Whoa, I can still change that letter. Any other questions? It's a good question, though. Yeah. Yo. Over R final. That's if they say, what's the potential, the final potential energy at that location. In other words, if they're not saying how much work. Yep. Anything else? Yeah. Sorry? Oh, thank you. I would have forgotten to do that. So on the first review, this one. Okay, a lot of the conceptual stuff like number 1. In other words, please make sure you know which direction is acceleration. Which direction is acceleration when you're moving in a circle? Toward the circle. Which direction is the force when you're moving in a circle then? Which direction is the acceleration? Towards the... And since force is mass times acceleration, what would make sense? Towards the center. Which direction is the velocity, though? That's always 90 degrees to the radius. That's what I tried to teach you, right? You're not actually moving or flying away. When you jump off a merry-go-round, you fly sideways, 90 degrees to the radius, perpendicular to the radius. The answer to number 1, for example, is x. It's going to go straight up. Questions that I like. Seven. 8. Hello. 12 that you just asked, but make it a written. 13. Something like 16, something along the Ferris wheel type of a question. Sure, 19. How would you find the gravitational field strength? Emily, I think you were the one that said it earlier. What's little g? What's the equation? Big G, big M over r squared. Now, once you know that, by the way, you have just found Mars's 9.8. It's not 9. You found Mars's G. Now for part B, you can actually go, oh, since we're on Mars, mg, little m. Anyways. Hey, you're back. 20 is good. $24 is good. 26 is good. 27 is good. 20, hello. Hello. 31 is good. 33. So 36, here's an example where I tell you the period and say, hey, what's the radius? I think this one you're doing cube root, if I recall. 38. I already said Ferris wheel, so 41. 43. 49. 49. What does it want you to find in number 49 here? Kinetic energy. It's a half mv squared. You know what? You're going to spend most of your time finding the orbital v. Did they give you the radius? Yeah. Are you in orbit? Oh, fg equals fc. You're going to spend most of your time finding v. In fact, this Shannon again, because actually kinetic energy is a half mv squared. I wouldn't bother finding v. I would find v squared and plug that in and just go with it. I think 50 is now fair game, not scholarship. The only reason it's scholarship is they went to the moon, but we did one a few minutes ago where I gave you the launch velocity from the Earth, and we figured out how high it would go. Okay, moon, different mass, different radius. $52 is fair game for that matter. Even though it's scholarship, it's fair game. I'm looking for one particular one, I think. Give me a second here. So I'm going to the older one. Bear with me. Some of these are kind of repetitive. Come on. Am I going to find one like it? Nope. Okay, there's a curveball, and I don't have an example like it, but we've done something similar. It's a multiple choice. I'll let you know what it is on your test, and it's one question. Don't freak. You should find most of this, though, reasonably, especially if you've done all of one review, especially if you've done both reviews. I was going to say no surprises. There is one curveball multiple choice. Yeah. Absolutely, there's a using principles of physics right to explain question. I think it's worth 3, and I snuck it in sometime today when you guys weren't paying attention or were paying attention. Okay? It's snuck in somewhere today. Guarantee it. Okay. Any other questions? So I'm around tomorrow after school too for Q&A. This was my formal big tutorial one though. Let me first of all stop the video, and then I'll ask if anybody wants a copy